And that is with each interior angle being 156. The easiest way to think about this, and this is just some enlargement of my polygon, okay? I don't know exactly how many sides it has, but this is just one side of it here, and it's telling me this angle is 156 degrees. Now, the easiest way to figure out the number of sides is actually to work, you can use the exterior angle. If each interior angle is 156, what's the measure of each exterior angle? 24 degrees. What's the sum of the exterior angles? Always? 360. So 360 divided by the number of sides equals 24 degrees. And we multiply both sides by 24, or by n, and divide by 24. And I get 360 by 24 equals n. I believe that's 15. So there are 15 sides. That's the trick. The other way of doing that, the harder way, is to use the interior angle formula. It's number of sides minus 2 times 180 divided by number of sides equals 24. Now that's a much more complicated equation. We can do it. I get 180n minus 360 equals 24n. I have to subtract 180n from each side. You get negative 360 equals, and I mean, it's just, I'm sorry, it's not, yeah, it gets ugly. So much easier to do it this way. Use the exterior angle. Okay? All right. Go answer your question. Go help your friend. Yes? 26. Is it possible for a regular polygon to have an interior angle with a given angle measure? Explain your reasoning. So 165. Kind of the same idea here. So if I have a 165 interior, that means my exterior is 15, which means my number of sides is the number of sides, and that comes out to a whole number, so that works. So yes. But if I say get to 75 degrees for an interior, that would make the exterior 105. Okay, so if I had an interior angle of 75 degrees, the exterior angle will be 105, and 360 over 105 is not a whole number. And I can't have like 3.6 sides or something like that. That wouldn't make sense. So the answer is no. So only if you come up with a whole number for the number of sides to work. Okay? Yes, Ms. Les.
So what are the answers for all of them?
So A was yes, be 24 sides. B is yes, it's 40 sides. C is no, and D is no. So 22, by the way, was 20. 20 was 160 and 20. I think most of the rest of them were pretty straightforward. Those are the only tricky ones. Okay. Anything else? All right, then let's take a look at today's assignment. We're doing today. And that is areas of regular polygons. We kind of talked about this briefly yesterday, but now we're going to formally define it. And this is stuff we've been doing over and over and again, just getting ready for this. We're finally formally doing this. When I have a regular polygon has parts called a radius, a center, and a special one called the apothem, which, yeah, sounds like an opossum with a lisp. It's an apothem. Some people say apothem. I like apothem better. Malin would like whatever I don't like just because she's a contrarian. See? Exactly.
No, I got a body put stuck in my straw. I don't care about you.
Well, there's a phrase I never thought I'd be hearing in class. Gotta say, occasionally there are just words that come out of people's mouths that you never thought you'd hear. I got a bobby pin stuck in a straw. It's way up there. But don't point at someone you're blowing because someone could lose an eye. All right. So that's going to go over well on the podcast. Okay. So. No one touch it. It's infected. All right. So anyway, the apothem, the radius, stuff like that. And inside any regular polygon, we get these right triangles. The right triangle is formed by the radius of the polygon. That's the hypotenuse. The apothem, which was this distance here. And the third side of that is half the length of one side of the regular polygon. That's my right triangle. And you know there are going to be multiple ways of finding this angle, these two acute angles. We can do it by finding each angle of the regular polygon like we did yesterday by using the exteriors, or we can use what's called the central angle. The central angle is formed by the two radii at the center. That's the central angle. And that's always 360 divided by the number of sides, the same as an exterior angle. In fact, the measure of the central angle is the same as the measure of the exterior angle. It's the same formula. So, different ways of doing that. This is half the central angle. Of the polygon. So all sorts of fun things going on here. The bottom line is we have to be able to find those parts so I can find the area of the triangle, so I can find the area of the polygon. The other formula we have for the area of a polygon is this one. Area equals the apothem times the perimeter of the polygon divided by 2. Now, essentially what we do in that formula is we put together all the triangles for you. So if we know the length of the apothem, we know the perimeter of the entire polygon. Now, by perimeter, I'm not talking perimeter of the triangle. I'm talking perimeter of the actual polygon. That's the perimeter we're talking about. Times the apothem divided by 2 because they're triangles. That's how we find that. Now, a lot of people don't use apothem times perimeter divided by 2. They do the triangle thing. They break it down in triangles, they find the area of the triangle, and they build it back up. In fact, that's the way I usually do it too. But we can use this formula as a bit of a shortcut once we know the apothem and the perimeter. It's really no harder or no easier to do it this way versus the triangle way. We got to do the same calculations either way. So let's take a look at it in action. Here I have a regular pentagon. Regular pentagon, I break it into its triangles. We note all 5 triangles it breaks into are the same. Now, this is different from the triangles we were doing yesterday. Yesterday we were doing the triangles for the angle sum, and those are the triangles that were formed like here with the green areas, okay? This triangle, and the third triangle in the center. That's not the kind of triangles we're doing now. Now we're doing central triangles, which are a little different. And we've talked about this before. I know if I go all the way around this circle, that's 360 degrees. There are 5 angles, breaking that circle into 5 angles, all of them the same. So 360 divided by 5 is 72. That's where my formula comes from. I'm also told that the length of one side of this pentagon is 8 inches. So if I so desire, I could know the perimeter very simply. simply, yes. Yeah, I can't talk today. The perimeter is simply 8 inches times 5 sides is 40 inches. So if I need to know that perimeter, I can get it. Yeah, go ahead. Now, this is what we're doing. We're taking one triangle out of that polygon. One of the isosceles triangles. The legs of the isosceles are radius of the polygon. This is the outside of the polygon. This side is 8 inches long. It's 72 degrees. We drop in our altitude. The altitude of this triangle is the apothem of the polygon. So if we went back here and drew that in, that segment, there's that apothem right there. Okay? Are you freaking out because it's such a fat line? Sorry, it wasn't perfect. We'll try to be better next time. People are very picky, you know that? Better?
No.
Would you like it dashed, perhaps?
Yeah. Dotted. No. Go to like the biggest ones.
How about that? Dashed and dotted.
Yeah.
Mm.
Make the point. Triangle. Go to finish. No, that's perfect. Perfect.
Okay.
No, you can't see a thing.
Yes, you can. You can get the left.
All right.
I have left.
Get some glass. All right. So anyway, that's the apothem. Now, we have to solve that right triangle in order to solve the apothem. Okay? So we've broken it down now. This is half the central angle, which we knew was 72 degrees, so that would be 36. Half 72 is 36. I know that this is half the side. The side was 8, so this is 4. And we need to know this side right here. What function am I going to use? SOHCAHTOA, we're going to use which one? Tangent. Tangent of 36, not TOA. TOA is not a function. Tangent is. Tangent of 36 is opposite of hypotenuse. So x equals 4 over tan 36. I'm sorry, adjacent hypotenuse. Or opposite adjacent. Opposite adjacent. Sorry. I said hypotenuse, but I said it upright. I said the wrong word. Forgive me. I said the wrong word. Try not to take me out and shoot me based on that. Okay. Okay. So 4 divided by tan 36. I get that apothem is 5.5 approximately. And at this point, I have a choice. Once I found that apothem, I could do one of two things. I could use that to find the area of the triangle. I could either find the area of this triangle or this triangle and then multiply it out by how many triangles there are. Or, since I already knew the perimeter was 40, inches, and the apothem is 5.5 inches, then I know the area is the perimeter times the apothem divided by 2, or 40 times 5.5 over 2 inches squared. So that would be 20 times 5.5, 110 square inches is the area of that big polygon. The other way we could have gotten that is we could have gotten that, like I said, we could have built it up too. We could have said, okay, the area of this triangle is 4 times 5.5 divided by 2. So the area of this triangle is 11 inches squared. And if that area is 11 inches squared, we could have built it back up. That means this triangle, which is 2 of those triangles, is 22 inches squared. And since that's 22 inches squared, each of these is 22 inches squared. And we put that all together, we get 110 square inches. So I could use the formula, perimeter times the apothem divided by 2, or I could break it down and build it back up. A lot of people don't remember the formula, so they just break it down and build it back up, which is just fine. It's a nice problem-solving method of doing this. Instead of memorization, it's problem-solving, which in some ways is a better way. Okay. Yeah. Oh, okay. That's just a continued solution there. So I didn't realize I had all these extra slides in here. Now, not every case requires us to use trig. We don't have to use trig in every triangle. In hexagons, we will not use trig because we'll have special triangles. In squares, we will not use trig because we have special triangles. In fact, squares are really super easy. If you think about a square for a second, a square is a regular polygon. But let's think about the apothem of a square for a second. The center of a square, right there, there's my radius. There's the apothem. What do I know about the apothem of a square? It's half the length of the side, isn't it? This is a 45, 45, 90 triangle. Okay? That's side over 2, half the side. Okay? The whole thing is, if the whole thing is x, this is x over 2. Okay, so the apothem is half the length of a side. So squares are really easy for us. I don't have a whole lot of work. If I just think through a square, I don't have a whole lot of work to do. The only thing that could be difficult here in a square is if they gave us the radius. But let's think about that for a second. If they give me the radius of a square, let's say the radius is 12 inches. Again, I don't have to work real hard here. If the radius is 12, how long is the diagonal? If the radius is 12, the whole diagonal would be 24. Okay, how long is the other diagonal? 24, and we could use diagonal 1 times diagonal 2 over 2 because a square is a type of a rhombus. I don't need perimeter times apothem divided by 2. Really, with squares, there's usually another way to do it that's a lot quicker than using the Polygon formula. So squares are kind of nice. We have multiple methods for squares. In fact, there's my square again. The equilateral triangle. The apothem in the equilateral triangle is a little bit tricky, but again, remember, in the equilateral triangle, each angle is 60 degrees. So when I start drawing in my triangles here, these are each 30-degree angles, and I drop that apothem in, again, I got a 30, 60, 90 triangle here that I can solve. In fact, for equilateral triangles, we have a special formula. And the special formula is this: side squared root 3 over 4 is the area of a triangle. Hold on for a second. I feel like my brightness is up again. Hold on. No, my brightness is way down. I just...
Turn it all the way up.
No, we won't be able to see anything. All right. And this is a formula that's going to be useful for us. Side square root 3 over 4. All right? This is one that people often like using. For an equilateral triangle, and we could prove this if we want using perimeter times apothem divided by 2, but I'm not going to worry about the proof right now. Let's just work on the formula itself. For an equilateral triangle, the area is always side squared root 3 over 4, where S is the length of a side. Now, that doesn't help us much if I don't know the length of a side, but if I do, it's really easy. And the way I remember that is because I can count to 4. Can you count to 4?
No.
Let's try it all together. Let's start with 1. 1, 2, 3, 4. 1, 2, 5. No, 3 so. Right. Okay. 4 is right out. All right. How? 1, 2, 3, 4. Look at the order of the numbers in the formula. S2, 3, 4. If you can count to 4, you can remember this formula.
But S isn't in the number.
You're right, it isn't, but we're reading S instead of 1, okay? Get over it. And the 2 is an exponent, and the 3 is in a radical, and the 4 is in a denominator. All right? So it's not perfect, but we can still help remember the formula by remembering how to count to 4. Okay? Side squared root 3 over 4. That's the area for an equilateral triangle. So really, equilateral triangles and squares are not going to be a big deal for us as far as regular polygons because we have special formulas for them. Square special formula, side squared, or diagonal 1, diagonal 2 divided by 2. Those are 2 special formulas we tend to use for squares. There we go. Ooh, that did not format nicely. Okay. Malin, just hush. All right. Hexagon is also special. The hexagon is always special. What kind of triangle is each triangle? Well, yeah. Each triangle here is an equilateral triangle, right? So again, with a hexagon just 6 equilateral triangles. So if I know the length of a side, I know the side area of this triangle is side squared root 3 over 4. So the area of the hexagon is 6 times side squared root 3 over 4 because there are 6 equilateral triangles. And the radius and the side are the same length, aren't they? So if they give us the radius, I know the length of a side. If they give us a side, I know the length of the radius. It's only in a hexagon. But hexagons are really special for us. In fact, the only way they can mess us up with a hexagon is if they give us the length of the apothem. But then we don't have a whole lot to do. We just find the length of a side, and we can do perimeter times apothem divided by 2 if we want. So equilateral triangles, squares, and hexagons are special polygons that are pretty easy to work with and do not require trig. All other polygons, pentagons, septagons, octagons, decagons, dodecagons, 23gons, stuff like that, those will all require trig. And again, there's the area of a hexagon formula. All I did for that area of a hexagon formula is I reduced the 6 and the 4 to a 3 and a 2. Most people do not remember the hexagon formula at all, but they can remember the equilateral triangle formula, so they just multiply that by 6. It's the same thing. This is a regular polygon. Find the area and perimeter of it. Radius is 5 centimeters. All right. So first thing I need to do is how many sides do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9 sides. Okay? So the number of sides is 9. Which means each central angle is 360 divided by 9, or 40 degrees. Which means that if I'm going to find this triangle, this angle is 20 degrees. and this side is 9. I need to be able to find the other two sides. I'm going to call them x and y. The only way to do that is going to be through trig. Somebody tell me, how am I going to solve for either x or y here? Pick one. We can't do both at once. Okay, y. Y is which side with regard to my angle? And 9 is the hypotenuse. Which one uses opposite hypotenuse? Sine. So sine of 20 is y over 9. So 9 times sine of 20. Oh, I'm sorry.
Oh, gee.
9 is the number of sides. Sorry. Because I was wondering suddenly where I got 9 also. So 5 times sine 20. No, 9. There are 9 sides. So that's about 1.71 for y. So this whole side is about 3.42. That's the whole side. So my perimeter, if I so please, would be 3.42 times 9, or 30.78. All right? Next thing to go for the apothem, which is x. X is which side? And that's the hypotenuse. Adjacent hypotenuse is cosine of 20 is adjacent over hypotenuse. So 5 cos 20 equals x, which is 4.70. 2 decimal places. So my apothem is 4.70. So the area, so now I know this is 4.70. Now again, I could build my area using either formula. I could do triangles, and I could either do the isosceles or the right triangle. I got to keep track of which one I'm doing, but however you want to puzzle solve this. Or I could use perimeter times apothem divided by 2, which is probably the easiest one here. So 30.78 times apothem of 4.7 divided by 2. So 30.78 times 4.7 divided by 2, 72.33. Centimeters squared. This is getting more complicated, isn't it? We have to be able to solve triangles and puzzle stuff out. This is not your one-step solution, not even close. This isn't just know a formula, plug the numbers in, and you got your answer. This is figure this out, figure that out, find this measurement. Now you can plug things in the formula. Then you can get things figured out. Obviously more challenging, but really when we're looking at this unit, this is the real big deal of what's going on. This is what we've been working on and working toward. So we've got some problems today. We're going to go back tomorrow. We're going to cover it some more. So you're going to do a little bit of practice tonight, just 6 through 18 on 765. Okay? That's only about a dozen problems, 13 problems actually. We'll come back. We'll go over those tomorrow. We'll review some more. We'll do some more examples so you get a chance to play with it. But this is why it's really important tonight, especially that you do your homework, that you practice this. So tomorrow when we come to talk about it again, you've got some practice under your belt. You know what you get, what you don't get. We can smooth out those rough patches. So then we review on Thursday and take the benchmark on Friday. You're all set to go. But there's no more new material after this for this week. This is all that's new. Just keep working on it.